to me, okay? Is everyone clear? Look, I can come out here, you know. I'm not, if anyone's not clear, John, are you clear about this? Gail, do you know how this works? You know how this works, okay. So, if someone's not clear, just tell me and I'll come back and help them. But anyway, we're gonna do a warm-up, and I'm gonna count down to 3, and then we'll flip to a camera where you'll be able to see how you voted. So you don't have to trust me, because otherwise you have to trust me, and I'm probably gonna lie. So here's your warm-up question. Yeah, yes, it is a very easy question. And there's no E. There's no E, so no, wait. Oh, you're too good. We're not ready with the camera. I'm going to count down to 3. You're too good. But there's no E, so there's no failing this class. I'm going to get my answer ready. Actually, I'm not sure because I haven't finished. I could still screw up. So I'm going to give myself a tentative B. But go ahead. On the count of 3, hold your cards up and we'll show you what you said. 1, 2, 3. There you are. Oh, my goodness. That's, we've got a few people in there. There's a few people who are pretty hard on themselves, but mostly you're doing well. Okay. And if we go back to, now I'm going to ask you a real question. So this is an analogy question. The age of the universe is to a human life as a human life is to what? And I'll give you a few seconds to think about it. Just prepare your answer so we can do it all together. And I'll count down so we do it all together, and then we'll flip to the camera. So think about that. Okay, that's enough. You're all smart. You can figure this out. 3, 2, 1, go. Very good. Wow. So you're right. It's a fraction of a second. Human lives are about 1 billion times less than the age of the universe. Actually, you kind of know all this stuff. I think I'm going to quit. I've heard they're serving some really good single malts downtown, so we could all get out of here early. But no, that was good. So the first lesson on the age of the universe is, of course, the vastness of time that astronomers have indeed pretty much probed. But let's return to what the universe is made of before we go back in time towards the Big Bang. We'll talk about normal matter first, the stuff that we're made of. 99.9% of the universe is hydrogen and helium. Rather uninteresting and the two simplest elements. Now, Phil Pinto in a few weeks is going to talk about the 0.1% that's left, but don't think of that as a residue that's uninteresting, because without that residue formed in the fiery heat of stars, we wouldn't be here. That includes all the nitrogen, carbon, and oxygen that life depends on, the heavy elements. So that's a critical part of the universe, but it's very important that stars exist, because if stars had never formed in the congealing gas of the expanding universe, the universe would have stayed hydrogen as helium. Now, you know, I'm a physicist, I'm not a chemist, but let me put my thinking hat on and figure out what you can make with hydrogen and helium. Nothing. You can't make anything with hydrogen and helium. You're going to make a hydrogen molecule, duh, and then you've got helium, which is inert. That's really dull. It would be a dull universe without stars, don't you think? That's the normal matter. That's the atoms. And look how many there are. One with 80 zeros after it. That's maybe the biggest true pure number in science, because that's an actual number of atoms. I know, I've counted, no, I haven't counted every one. Nobody has counted every one. It's an estimate, but it's pretty good. But it's actually eclipsed by a factor of 1 billion by the number of photons in the universe. There are 1 billion photons in the universe for every atom. That's an interesting fact, which will be fully explained, I think, by Mike Turner next week, but I'll allude to where it may have come from. Something we need to explain about the universe. Most of those photons are unnoticed by us because they're dim microwaves that I'll talk about in a few minutes. And those atoms, those 10 to the power 80 atoms, are agglomerated into 100,000 billion stars, 10 to the power 23, which typically are parsed 100 billion per galaxy. And there are 100 billion galaxies, round numbers, in the visible universe, the universe we can see with our telescopes. So there, in a nutshell, is what the universe is made of. That's a lot of stars and a lot of galaxies. And just to put a little forward light onto Carolyn Porco, the last speaker in this series, she's going to talk about the proclivity of the universe for life, and she's going to talk about the way we search for life in the solar system. Our technology only lets us look for biology in our backyard so far. But what you should realize is the cosmic number that, based on the census of Earth-like planets with the Kepler telescope and what we know from our backyard in the Milky Way, the best guess is that there are billion Earths out there, more or less, Earth-like. That is an incredible number. And so you have to ask yourself the question, since life started on the Earth almost as soon as you could imagine, when the conditions were really inhospitable, do you imagine that all of those billion Earths out there are sterile and there's no biology in any of them? Or put another way, how many of them do you think have spawned some interesting biological experiment, perhaps even eclipsing the intelligence and complexity of life on Earth? Wouldn't that be nice to find out? But that's the cosmic context for life in the universe. And these galaxies are real. We can observe them with the Hubble Deep Telescope. The galaxies you see panning across this tiny region of sky are all 10 or more million times fainter than the eye can see. Each of them is within 5 to 10 billion light years away. So you're looking at ancient light. And as you look at them, each of these galaxies has roughly 100 million Earths. You can imagine the possibility that on some of these galaxies across the eons of time, someone or something is looking back at us. Each fuzzy smudge is a galaxy, a distant system of stars, seen with the Hubble Space Telescope in the deepest image ever made. That's the normal matter. But in a surprise to astronomy that's now 30 or 40 years old, so astronomers have gotten over their surprise, the universe is made of 6 or 7 times more dark and mysterious material than the light and visible stuff that we're familiar with. It's called dark matter. It's seen here not because we can see it, but this is a computer simulation where we try and understand the universe by spooning dark matter with the appropriate properties into a computer and seeing how it structures over time. But the dark matter itself is invisible. So how do we know it's there? Good question, and was answered painfully by astronomers over several decades. We weigh galaxies by looking at star motions. Now, if you looked at the motions of stars near the sun, they're just milling around randomly because the little cube within 100 light years is partaking in a leisurely quarter-billion-year orbit of the center of our galaxy. But if you map out the motion of stars across the entire Milky Way, you see a pattern of rotation which should have a particular character if the mass of the Milky Way is where you see the light, which is where the stars are, which is what you expect. What astronomers saw, starting actually 30 or 40 years ago, was something quite different. Again, if a galaxy's mass was really just where its light was, then by Kepler's law, you would expect the velocities of those peripheral stars to start to decline because you've seen past the mass. Just in the same way that moving out from the sun, the velocities of the planets all decline to the outer planets. What was seen was not that at all. The velocities continued high, even rising beyond the distance of the sun to the outer edge of the Milky Way. Not only in the Milky Way, but in every spiral galaxy ever observed. This is a universal phenomenon as far as we know. And the only sensible explanation for this in terms of gravity is that the mass of a galaxy, if you just look at its stars, you're underestimating by a factor of 6 or 7. And that larger factor, additional, is dark matter. The second way we've measured it, very convincingly, is by gravity-bending light. If you look at a distant galaxy through a cluster of galaxies between it and us, mass bends light according to general relativity. And so the light of those distant galaxies is stretched, sheared, and amplified into little arcs of light. It's a very striking phenomenon. Can't be explained any other way. This gravitational lensing, as it's called, a prediction of general relativity and a confirmation of general relativity, is a way of weighing a cluster and also individual galaxies. And it confirms what motions of stars do, that galaxies are dominated by invisible matter. And the question becomes, what is the dark matter? And all I can say at this point, but we're optimistic within a decade we may know, is play a game of elimination. First of all, why not question your theory of gravity? And people have done that, to be fair. The point is that the gravity law, and that is Newton's law on large scales and Einstein's law when gravity is strong, has passed so many tests that we're unwilling to throw it away, because then you throw everything away. And so the hypothesis has become that there is a dark form of material in the universe. You can only make the universe in a computer look like the universe we see if you put dark matter into it. So far, all we've done is eliminate things. Well, black holes are dark. Maybe it could be black holes. No, because before you have a black hole, you have a supernova, and that's a pyrotechnic display that would be easy to find. Maybe they're just dim normal stars. No, our stellar census with things like the Hubble is just too good. You can't hide dim stars in sufficient quantities. Because remember, you need 5 or 6 times more than normal stars. What about things that are just too low in mass to turn on, to ignite in fusion, and so they don't shine, so they're dim? Dark things like brown dwarfs, or even planets, free-floating planets, can't do it. Once again, gravitational lensing would find the signature of those if they were in that large number, and that's ruled out. And then you can go all the way down to mountain-sized boulders in space, to things the size of your fist, to microscopic dust grains, just littering space. And indeed, those things would be very faint if no nearby star, hard to see with a telescope, but those are actually ruled out because they would still be subject to the ambient radiation of stars, and they would radiate in the infrared, and infrared satellites have convincingly ruled this out. I mean, if you look at what we've done, we've ruled out dark objects all the way from black holes down to microscopic grains of dust. All that's left is subatomic fundamental particles, and that's where the game is. Mike Turner will talk more about this next week. Time for a little more audience participation, this time on the size of the universe. You've done the age, so now it's time to do the size. I don't have to explain it. You know the drill. So let's make a model of the universe, just to give you a sense of it. Centennial Hall is the Milky Way, 100,000 light years. Just use your powers of estimation to guess how big the universe is. And just remember, in this model, each of you is standing in for 100 million stars, which is pretty impressive. Yeah, okay. So you all know, you're all quick with this, so we'll just count it down. 3, 2, 1. Whoa, very good. And you're right. So the visible universe, just the visible universe, would be that enormous size. And that's sort of like the Earth. That's 10 times the radius of the Earth. So imagine a volume which is 1,000 times the volume of the Earth filled with things the size of Centennial Hall, and that's the observable universe pretty well. Okay, good. So I think the message here is ignominy, to use a word, mediocrity, whatever. We are on an average planet orbiting a mid-sized star. Our galaxy is unexceptional. We're on the periphery of a kind of mediocre, not that impressive cluster in an undistinguished corner of a ridiculously large universe. And so, you know, this is part of the punchline. There's you, and there's the universe. We're insignificant. Get over it. Let's go back to the Big Bang. Enough beating around the bush. We have expansion. Hubble's first discovery that external galaxies were there, distant systems of stars expanding the known universe, would have been enough to make him the most famous astronomer of the last century, but he made a second discovery close on the heels of his first discovery, and that's the cosmic expansion. Hubble observed the spectra of galaxies, shown in the visible spectrum just turning light into a rainbow, and then represented graphically where you track the wavelengths of the sharp emission or absorption features of the elements that galaxies and stars are made of. And when you do that, you find that the distant galaxies, the external galaxies, are always shifted, very, very occasionally to the blue, but almost entirely to the red, to longer wavelengths. And sometimes, as in this case, by a significant fraction of the speed of light. So they're moving away very fast. Beyond that, he showed a linear relationship between the recession velocity, the speed of moving away, and it's a large number, 1,000 kilometers per second there, and the distance. MPC is megaparsec, that's 3 million light years, so you're going out to 6 million light years. It's not a very good correlation, but that was his first data, and it established the idea of an expanding universe. Since then, we've expanded Hubble's relation by factors of 100. Hubble's original relation, that previous graph, is the little blue dot that would fit near the origin here. With modern telescopes, we now extend the regime out to 1.5 billion light years, and the perfect linear relationship holds. The expansion, the cosmic, linear, smooth, expanding universe is valid on huge scales of the universe. And it logically begs a question. If everything is moving away from everything else, what happens if you run the clock backwards? Surely there was a time when all the galaxies, now further apart than ever, were all on top of each other. And since the universe behaves in some ways like a gas, the universe must have been smaller, hotter, and denser. You also have your first check on this idea. because we know how to measure the age of the oldest stars in the galaxy. And on the principle that you should never eat anything bigger than your head,